Good morning. Here is the slide that we finished with yesterday. Before we now move on, maybe you have questions. Okay. No questions? No. All right. So, the last thing I mentioned yesterday was this long term. So that the Nordtest method, or in general, the so-called single lab validation approach, of which Nordtest is one of the realizations, it works long term, so that in this slide, which you I think well remember, you've seen it now in several times in different contexts. In Nordtest, we operate here. If you remember, then with the ISO-GAM approach, we actually operated largely up here in this short-term area, but in Nordtest, we operate in the long-term region. And of course, what holds very well, I also already emphasized, the longer is the time frame, the more effects change their status from systematic to random. So that the long-term intermediate precision enables taking into account a number of effects that within a day would be systematic, but in the long term become random. And in a way, I have the way this is here pictured, essentially see all these things here within a day are systematic things, but in the long term, they travel into this green block, meaning become random. Okay, now you already saw the main equation, but now I have rewritten it with the terminology in the Nordtest guide. This is how Nordtest guide pictures these components. So this U and U are, of course, standard uncertainty. R is reproducibility and W is within lab. So this is what this RW means. And bias, of course, is bias, meaning the systematic. And then, I think these two boxes actually don't give anything new. You've already heard this. So long-term random effects sit here, and possible laboratory and possible method bias sit. Again, possible because in many cases, we actually cannot be sure whether we have bias or no. Now, what I already explained, but let's see whether you remember. You see that there is here written laboratory bias, and method bias. What do these terms mean? Laboratory bias, method bias. We already encountered them. We've discussed actually. Could you take the microphone closer?
Temperature.
Would you give somewhat more general answer? Temperature is like very specific, and I don't fully follow how temperature fits here, but maybe I'm just misunderstanding.
For example, somehow the temperature affects our results. So in different labs, there are different like air moisture temperature will output different results.
Okay, so what you mean is that in our lab, always the temperature is sort of very low or very high. Is this what you mean? Okay, yeah. This sort of makes sense, but in fact, in laboratories also the temperature tends to differ. Yeah? In summer it is typically warmer, in winter it's typically colder. But now could you, Maitan.
Maybe the lab could be obtained by different measurements, repeated measurements, and compared with maybe a reference substance or a reference material, and the method is the one that is reported by different calibration tests or something that has or certificates.
I don't understand. This might be, of course, me who's stupid. Yeah, this doesn't. You said wrong. But could you, Maitane or Balong or anybody on the web give somewhat more general answer? Yeah, Claire, please.
The first thing that came to my mind is that laboratory bias means that bias we get from the specific method from the specific laboratory, and method bias refers to the general bias of the method itself, disregarding the laboratory whatsoever. So it's not dependent on whether it is done on this lab or someone else.
This is, pretty good. But now, what is important about it in this context?
Those are two separate uncertainty components.
Not necessarily. It is very rare that people try to separate them somehow, or try to find what is laboratory, what is method bias. Actually, oftentimes this is handled as one single component and turned lab and method bias. Yeah, so this can also be one thing. But I still haven't heard one phrase that I would very much like to hear. So what makes this bias different from any other bias type or any other kind of bias? In the context of this uncertainty evaluation. I'm asking maybe too simple a thing. It's very, very simple answer. Sort of, yeah, but can you say something more?
If we are considering like laboratory and method bias, it will be considered in a long term. Like even if it's the long term, it will be considered as like systematic one and not be like a random one.
Okay, yeah. You now more or less said it. So this is the type of bias that never goes away. However long you make your experiments, yeah. And actually, I have even written long-term bias and in brackets lab and method bias. So this is the kind of bias that was always there as long as you use that same method. So for example, maybe your digestion procedure always leaves some amount of element not dissolved, so you always lose some, yeah. So it's always negative. You are always negatively biased. Or maybe your extraction procedure is not 100% efficient for some organic contaminant, which is very common actually. Yeah? So that always you have slightly less in the final solution that you put into the instrument than was originally in the sample that you took for sample. Okay, Hans says, let's see, laboratory bias can have a higher contribution, but it's something that we can correct. Yes, Hans, we can correct. In this section, in this Nordtest method part, or Nordtest uncertainty method section, I'm not explaining correction at all. Here, what we will do is that, okay, that long-term bias might be there, but again, I cannot stress enough, in most cases, in the majority of cases, what you end up with, in most cases, what you end up with is possible bias, so that you don't actually know whether you are biased or not. And if it is just possible, you should not really correct, because you can make your result more wrong than it initially was. Yeah? But later on, we will have, I think it was in reference material section, a separate subsection of bias or recovery correction, whether to do that or not. And we will look at the kind of a roadmap or chart, decision tree. I think it's called decision tree. How to decide whether you should correct for bias or not. Hans, did I answer your first question? Okay. Now Hans says, I remember our example before was the poor calibration of the oven for gravimetry. Yeah, again, yeah, this can be, again, a lab bias, in the sense that if this is the oven you use for years and years and years, then it always remains the same. But of course, if that oven is maintained from time to time, or maybe you buy a new one and so on, then it can leave this section of method bias, because then you have a new oven which maybe is calibrated differently, and now maybe you're heating too much, while previously you maybe heated too low. Okay. Let me stop for a moment, maybe still question. No. All right. Then one more thing. You remember we have already touched upon absolute and relative uncertainties, and I warned you that we will come back to that. And here now, this will be a big topic. So in Nordtest uncertainty evaluation, it's up to you to decide whether you use random between absolute or relative uncertainty. And we will see about that, yeah. And now, what the Nordtest uncertainty estimate means. If you recall now our acidity example, there you did put in exactly the same data of that sample. Okay, these three replicates, yeah, the milliliters were like this. Okay, you pipetted 10 milliliters of the sample. So all the information from that specific analysis on that same day was in there. So that the result that you got, the uncertainty that you got, was really for that specific result on that specific day. But Nordtest works very differently. You see, the data that you use in Nordtest are actually not directly related to your analysis of this specific sample that you do here now today. So that what you rather do, you get some kind of average uncertainty of your method. Get what your method's uncertainty would be on an average across those many samples. Yeah? And then you take this uncertainty, yeah, and assign it to your today's result. You will simply say, okay, today my sample is this, my method uncertainty is this, so now I take my method uncertainty, I take my today's measurement value, and I put them together. So that you assign this long-term or average uncertainty to your today's result, even though this uncertainty may be calculated in such a way that no data from today are involved at all. So it's possible even that way. Or maybe one point on the X chart is from today, everything else is from the past. Yeah. And the specific way how many milliliters of sample you took, how long you did some shaking, extraction, that does not enter this calculation at all. So whatever you do today is assumed to be similar to what you always do, so that the average uncertainty of the method can be applied to today's situation. So that these meanings are quite different, really. Yeah? Now, Louis is asking, is laboratory bias associated to differences between labs, or is it just one lab? You know, Louis, laboratory bias, first of all, refers to difference between laboratory value or average, let's put it correctly, average of laboratory values and some reference value. So that different laboratories can be biased differently. So it's not just one lab. All labs can be biased to some extent. Some might be biased higher, some might be biased lower. I'm not sure if I got your question right, but I tried to answer. Okay. The bias component can be evaluated differently, as we will see in the coming slides. But let's say the most common way to do that is analyzing a certified reference material or doing spiking. And both of those you can do just in your laboratory. You can also do it by interlaboratory comparison, yes. Okay, now we will come to that. Now, how to do it. All right, now, absolute and relative uncertainties. How do we choose? Now, typically, what happens is that in today's sample, the analyte concentration is not the same that in all of those data that you use for uncertainty evaluation. For example, you today might have something like 20 micrograms per kilogram of some contaminant, but maybe your control chart is made at 50 micrograms per kilogram, and your certified reference materials that you used for bias might also be different. Yeah? For that reason, it is not automatically clear whether, for example, certified reference material analysis at different concentration level automatically applies to the concentration level that you have today in this sample. And the question to ask then is whether we use absolute or relative uncertainties, and the answer is here. In general, whichever is more constant with respect to analyte concentration. So that, for example, if your analyte concentration increases 5 times, and your absolute uncertainty also increases 5 times, then what happens to your relative uncertainty? Remains the same, exactly. And in such a case, you should, of course, use relative uncertainty. But it also can happen that your analyte concentration changes 5 times, but the uncertainty remains pretty much the same. Then you should use absolute uncertainty. This whole question did not emerge in iso-GAM method at all, because then you had all your specific input quantities and you assigned to each of them their own uncertainty, of course, in the same units in which they were measured. But here, since you are calculating some generic uncertainty for the method and then applying it to an individual sample, then this question immediately emerges. Some rules of thumb are here. At medium and high concentrations, usually relative uncertainties are more appropriate. At trace level, near detection limit, very low concentration, usually absolute uncertainties are more relevant. But the best is, let me again stress, now let's take some also. The best the best is, of course, to check which one is more constant and use that one. We will see that in our calculation example. Here now is the steps, or are the steps of the Nordtest approach, but there's not really much to explain here. Most of these steps are very similar, like specify the measurand, convert the components to standard uncertainties, and so on and so forth. And they, like, let's say the really like significant steps are here, and they of course are exactly evaluating exactly these two quantities that we, or these two uncertainty components that we already discussed, URW and U-bias. And yeah, and what I already said, yeah, average uncertainty of the method, which you then assign to your result. And now let's see, how do we evaluate this URW and U-bias? How can we do that? So URW, yeah, long-term or uncertainty component that takes into account long-term variability, and its value, or it is evaluated as within lab reproducibility. So if you remember, I praised this within lab reproducibility in all possible ways. That's so important that we will use it and so on. So here now you are, here we now really are. So that this URW component essentially is this. Very simple. Now, how do you determine it? Now, first of all, you have to have some, like, let's say, test samples. Of course, the analyte has to be the same, yeah, as what you're analyzing. And ideally, it should have the same sample type, similar matrix concentration and homogeneity to what you have in your routine samples. And you can use pooled standard deviation. And of course, it's the same laboratory, the same method, yeah, but it might be different, or it certainly is different days, different persons, might be also different batches, and anything else can differ, which typically changes in a lab. Most commonly, this uncertainty source is evaluated from so-called control charts or X-control charts. That will be a separate topic in this course later on. Let me now just say that it essentially means the following. You prepare a batch of some kind of sample, like soil or meat or blood plasma or whatever it is, in sufficient quantity that every time you run your method, you can take a subsample from that batch. So it has to be oftentimes pretty big, might be several kilos of sample, yeah, so that you would have enough for a long time. You homogenize well, and every time you run that method, you take one sample from there and put among your other samples. If you now remember, we had on several occasions in the slides this exemplary sequence, yeah, with the calibration samples and customer samples. There were also samples CC, which I termed control chart samples. So those are the ones, yeah, that you. And if you have many data for that specific control chart sample, you can calculate the standard deviation. And that standard deviation will be the SRW. It will be the within lab reproducibility. Very easy. So that URW is pretty easy thing to determine, especially in those labs which can get sufficient amount of sample when it can be stored sufficiently long. yeah, and can be made sufficiently homogeneous. And these are important points. Any questions?
I understand the theory of within lab reproducibility, but like how many replicas each year we have to conduct?
Yeah. I would say that in the case of within lab reproducibility, it is usually more a question for how long time than for how many replicas. As I'm saying, preferably 1 year. Suppose this method is used twice a week. Suppose it's a routine analysis lab which uses this method twice a week. The year has 52 weeks. So if you do it for the year, you will have 100 replicas, which is far enough. In principle, I would say if you have already 30 or more, there's no question about number of replicas. I would say even 20 is pretty good. So for example, if the 20 replicates are spread across the year, pretty okay. But again, quite often in really routine labs, and in some labs, some methods are run every day. So there are 5 working days a week. Yeah, it's 250 something working days in a year. So they have cosmic amounts of replicates. So the replicate number is not so important. I mean, it is very important, but it's very easy to get under these conditions. What rather happens is that the amount of this control sample has to be really big, yeah, if you run it so often, unless it's a non-destructive method. So, of course, those people are very lucky who run something like XRF, for example, where you can use the same metal block for years and years. You don't consume it for the measurement. Yeah, you use it all the time. Then it's extremely good. But if it's some bioactive thing in meat, then you have to prepare several kilos of meat and put in freezer, and it's more difficult. Yeah, Mike Tanner?
I think that you have already explained one time this, but I'm confused now. Like this control sample must be prepared every time that I'm gonna carry out the analysis, or just one time with a big, I don't know, like I take a huge amount of sample and then just take a few sample every time, few part of the sample every time, or I have to repeat the whole procedure every time that I'm gonna carry out the analysis.
Yeah, maybe I have done a lousy job. Yeah, not explaining well. So yes, every time you must do sample preparation also. Clearly indicated here. But what you do, let's say you take 5 kilos of meat, suppose. Now you mix very well. You have to be able to mince this 5 kilos of meat very, 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 make it very homogeneous, so that let's say it's fat content in meat. Yeah? So that this fat content in all parts of the meat is exactly the same. Now, if you put meat in freezer, it will be like one big chunk, very difficult to take subsamples. So what meat factories have done, for example, they take these small plastic bags, which you can see, and they put like 10 grams into that bag, into freezer, another 10 grams, yeah, and into freezer. So there will be small plastic bags, many tens, maybe few hundreds in the freezer. And every day you take one of those subsamples, one of those plastic bags, you melt it, thaw it, bring to room temperature, and then do sample preparation as if you would do with your any normal sample, and include it as control chart. Did I? Yeah, the first homogenization has to be done only once with this big amount. Yeah, that you cannot do every. Then it does not make any sense. Yeah, that is done just once, and then afterwards you simply take subsamples. Of course, it's much easier with drinking water or something like that. But yeah, in principle, with very few exceptions, almost everything you can work this way, except in cases when the sample amounts are so small. Like I think I've been here giving the examples of newborn babies, from whom you cannot get sufficient amount of almost anything. Yeah? But then, of course, on the other hand, if you analyze blood of newborn babies, it's quite possible that the blood of adults is also okay as a control sample. Yeah? It's not so different finally, because the humans and humans, yeah, although one human is very small. Yeah. But blood of adults is available in liters if necessary. Yeah, there are blood centers in hospitals, and of course there's always this ethical thing, yeah, and whether you can get in, whether you are allowed to work with it, and so on and so forth. But those labs who do that kind of work, they have all those certificates. They can do that. Yeah. Okay. Anything else?
Before we go on to how to determine the URW and Q bias, I just want to clarify this concept of NORD test, that we can use the NORD test approach even if is it right? Even if it is not our data? Or
no,
not really?
No.
Because, for example, you are a starting lab without much data gathered yet, or you're just a researcher that doesn't do it routinely, but you wanted to have an uncertainty right away, so you use a NORD test approach. And suppose you use a standard method that has this precision and method bias already there. Is it okay to use that as your initial measurement uncertainty, and as you go along, as you progress, as the time pass, you revise on it, or what? Yeah.
A very brief answer would be simply no, but let me give slightly longer answer. So, in any case, both of these things here assume that it's your data. These here are the ones which where you don't use your data, and as I said, I would only dare to recommend them in such a case when you don't have that analysis. Now you can say and write this out, okay, but when I'm only setting up, where do I get these 30 replicates over 6 months? But usually, I think you cannot set up a method with less time than, say, something like 1 month. And then at least, let's say, 2 to 3 weeks from the latter stage of setting up and polishing your method, you already have something which enables you to run samples. I would already then start a control chart, prepare some sample, yeah, and run it all the time. It also is very useful thing for during still method development, when you still adjust and make adjustments. And when you are finally ready to start serving customers, you might have perhaps SRW from 3 weeks and let's say 10 samples altogether. That I would consider a suitable initial starting point with which you already can present results, perhaps even artificially making your uncertainty slightly high as you're not yet so sure in yourself. Yeah, but I would not take data from not really. But what I very much agree with, and what I very much like with what you said the phrase, and then revise. And this is my favorite sentence in this whole course: never stop. All the time add new data and calculate better and better and better and better estimates of all those things, and make your uncertainty estimate more and more and more and more and more relevant. And also, for example, bias. When you determine bias with just one CRM, this is something I would not recommend. But you can already start offering services. And then you make efforts to find another certified reference material, or maybe find some expert lab or whatever means to have more bias estimates. You can put more and more and more in and get better. Did I answer? Okay. So yes, in the initial stage of a new method, yeah, you cannot yet have 6 months and of course not 12 months of data, but that you can get later. All right. So we were here, yeah. And here, of course, two things which again are pretty understandable. This control sample has to cover the whole analytical process, which is essentially the same as said here. So that every such subsample should also go through sample preparation. It's not okay that you just do sample preparation with a huge amount of sample. Now you have a solution, and now you put that solution every time as control chart. And then what's a difficult one here? Ideally, if you run your analysis with different matrices or different concentration levels, you in principle should have different control charts. I'm saying in principle because it will get out of hand very quickly if you want to be like dogmatic here. Suppose you are a food control laboratory, which determines pesticides in fruits and vegetables. And in this country, we don't have so rich selection of fruits and vegetables, but I think probably in maybe Philippines or in Vietnam, probably you have more different fruits and vegetables in your shops than we do here. But even here, I think if you go to a shop, a bigger one, you can easily find, let's say, something like 40 to 50 different fruits and vegetables. They're starting from potatoes and carrots and ending up with kiwis and whatever they are. And now, suppose you have a food control laboratory, and every day inspectors can bring a new kind of thing for you. Today it's a tomato. Next day they will come with kiwi. Then they will come with orange. Then it's an apple, and that's on and so forth. In principle, for every fruit and vegetable, you should maintain a control sample, yeah, and then run control chart and so on. But now if it's 40 to 50 and every day you should put in 40 or 50 control chart samples, you almost don't have any room for any customer samples. Moreover, different concentration levels. Yeah? Okay. Yes, here we perhaps could say that let's keep just two, yeah, very low and high, yeah, that's fine. But then we would be up close to 100 control samples every day, which is absolutely unmanageable. It just cannot be done. Yeah. So this is why I'm writing here, ideally. Please note here, I don't write ideally. No ideally here in this box, yeah? But in this box there is ideally. Usually what people do in such cases, they take some representative matrix. And luckily, in many laboratories, the diversity of sample matrix is not so big. Suppose if you are let's say some factory producing some meat or maybe bread or maybe sausages or whatever, then your factory has very clear things that the factory produces. So unknown new things don't really jump in unless, of course, there's some product development. But then those products also usually are pretty well known by the factory and then how similar they are. And so forth. Then secondly, in many cases, there is the lab can do lots of different things, but the sample matrix is not so diverse. For example, all those drug studies or studies of pharmacokinetics and pharmacokinetic studies when drugs are developed. Very often the matrix is essentially blood plasma and then also blood plasma, although the very different drugs and then so on. So again, you don't have so different matrices, although you may have different analytes. In the case of fruits and vegetables, I did not mention that there are tens of different pesticides that can come under question. Of course, for all the different pesticides, you don't need to have separate control sample for every pesticide. You can have in one control sample a number, yeah, if your method enables to separate. But nevertheless, it makes still more and more data. I will later on in the reference material section, I will or we will discuss matrix types and how can we classify matrices and what could be like representative matrices for different foodstuffs and so on, so that you would not go crazy with all the different matrices. So that yes, oftentimes, sadly, we need compromises here. Okay. Oh. Now, bias. You have to take into account possible bias of your average result from the best estimate of a true value. And best estimate of a true value, of course, is some kind of reference value. The reference value of certified reference material, or maybe value how much you spiked into some sample, etc. Again, you of course have to include sample preparation, yeah. And bias is always determined from replicate measurements, because bias always refers to difference between reference value and average value of your result. Yeah? So you never can get bias info just from one analysis, because this analysis result is influenced both by random and systematic effects. And now, for determining the bias, the key issue and the main headache is that you need a reference value. And this is what makes it much more problematic than URW. In URW, you don't need a reference. If you have your pile of meat, you don't need to know how much fat is inside. You can still use it for the control sum. Yeah? You simply see the variability between. But for bias, you need a reference value. And reference value can come via different routes, but 4 different situations are here. I think I mentioned them already to you in one of the lectures, but it's not so bad to mention again. No? Possibly the best approach would be that you have your samples run with some high-level reference method, for example, in some top laboratory. Yeah? So you have your own result for your sample, or you split your sample, you analyze one part yourself, the other part you send to the other lab, and now you compare the results. Yeah? Of course, you have to analyze it several times. Yeah, the other lab also has to analyze it. Yeah, and this would be very good in the sense that this bias would really correspond to your actual samples, really the same matrix. Sadly, most of the time you don't find such reference lab or such reference method. It might be extremely expensive to have it analyzed there. So this is rarely possible, although it's a very good. You might also say, oh, okay, but let us set up a reference method ourselves. Good, yeah, we can. But then this comes the question, okay, but perhaps then we could already analyze all the samples with that reference. Why do we have that bad method? Of course, sometimes it can be that reference method is very expensive to run. Yeah, you only don't want to run it so often. For routine customer samples, you use some cheaper method. Then it makes sense. Yeah, and there are some situations when this is actually pretty reasonable. So many. It's not very common. Yeah? The next possibility, which is either the best or at least one of the best, is analyzing certified reference materials. So certified reference materials essentially are carriers of reference values. Some metrology people sometimes say that when you buy a CRM, you are buying a value which simply comes with the material. Yeah? So material is just a carrier of that value. So that the valuable thing is the value, not the pile of meat or milk powder or soil or whatever. This is true, actually. In a CRM, if it's a milk powder CRM, the milk powder costs almost nothing compared to the fact that it has been analyzed, it has this has this. Okay, certified reference materials, of course, have the problem that they are available commercially only for fairly common analyte matrix combinations. Whenever you do some cutting edge research, you usually don't find the CRM. Secondly, in CRMs, always the problem remains that your matrix might be somewhat different to what the CRM matrix. I've brought here frequently the soil as an example. Yeah? So if it's a soil CRM, yeah, but even in this small country, there are 20 types of soils. Which type it is? Yeah, not so clear, not so easy to see. Okay. Then the next possibility is from interlaboratory comparison. This is what Lewis asked. Yeah? And indeed, at high level or good level interlaboratory comparisons, the consensus value from labs can be considered a kind of a reference value. Usually not as good as a CRM reference value, but still. So that you can participate in interlaboratory comparison, you get from there a sample, you can analyze many times, yeah, get some average value, you submit it to the organizers. We will have interlab comparisons, a big part of this course later on. So I will explain how all that is done. And then you can see, aha, I'm lower than the reference. Okay, this is my bias. But now, of course, interlaboratory comparisons, you cannot order them in such a way, okay, I would like to now to participate in interlaboratory, because now maybe nobody organizes. Yeah, they organize in every now and then. And again, it's only usually the most common analyte matrix combination. You do some strange type of work, you don't really find an intercomparison. And also, most intercomparisons are so-called proficiency testing exercises, which means that any kinds of laboratories participate. Also laboratories which are not really good, which means that occasionally the average value or consensus value from labs maybe is not the best. Yeah. True, that's not very big problem, but still, yeah, it still is a problem. And finally, spiking experiments. Spiking, we will come to that again. There will be a section in this course about spiking. Essentially, you split your sample in two parts, you analyze it as it is, and then you add to the second part a very well measured amount of the analyte, and again you measure. Now, of course, the second result will be bigger than the first result, but how much bigger has to be essentially by the same amount how much you added. But if it's less bigger means, some analyte is lost. Yeah, so you have negative bias. Spiking has the beautiful property that you can not always, but you can run it with exactly the same matrix as your samples are. So matrix matches is very good. But sad thing is that in many types of materials, you simply cannot spike your analyte into the material the same way as the original analyte is in the original. So suppose you analyze lead in soil. How do you spike it? Part of lead in soil might be inside sand grains at times. So you cannot squeeze more lead into sand grains. Part of lead might be inside some plant remains. But when you do spiking, that lead simply will be, maybe you put lead nitrate or whatever you use for it, it will be covering those materials. So your spiked amount will be typically extracted or will be typically accessible much more easily than the original analyte in the sample. This is not the problem for homogeneous samples. So drinking water, beautiful, no problem at all. Blood plasma, beautiful, no problem at all. But soil, rocks, minerals, or maybe wood chips, for example, or glasses. How do you disperse some element into glass? Yeah, if it's a piece of glass. Not really clear. Okay, with glasses, there are some approaches. You can fuse them, melt, yeah, and then put some other mineral in and then mix. So it can be done, but it's also not so easy. So spiking you can do yourself. You are not dependent on anybody selling anything, but you cannot really do it easily for all. As you see, there is no ideal way for determining U bias. And this is why we are always very happy if as many as possible uncertainty sources are not within bias, within this URW or within lab reproducibility, because that one can be determined. And ideally, you should use several CRMs or several proficiency tests or several spiking experiments, or in any case, try to get bias estimates by several means. And don't be surprised if one way gives you negative bias, the other one gives you positive bias. And what that means exactly what I'm always stressing here. It's about possible bias. Your method actually might not be biased at all. You simply don't know. And the uncertainty, this U bias uncertainty, to a large extent evaluates your not knowledge of the bias of your method, whether you have it or not. As I mentioned already yesterday, this true leads occasionally, I would say, not rarely, to overestimated uncertainties with the north test approach. Of course, maybe there's no bias at all, but you think, still there seems to be, so I put an additional uncertainty, while in fact it was not needed, So, questions here. This slide is very information rich. A lot to discuss. I see Luis is typing. Let's see what Luis is saying. Gleb. Okay, Gleb. Yeah, you can ask. While Luis is typing, you can already ask your question.
I wanted to clarify these intra-laboratory comparison measurements for myself. So let's suppose I get value and some other lab gets higher value, and I do bias determination from that, then I just assume the reference value somewhere in the middle, and I have negative bias going in this direction, and they have the same amount going in the opposite direction. That's how you do it.
Yes, in principle, yes. In the case of interlaboratory comparisons, you are not comparing yourself against individual labs, but against consensus value, which includes values from all labs. In simple case, it might be simply average value or mean value of all the lab results. In more complex cases, there can be more complex. But yes, this consensus value is what is considered then the, let's call it, the best estimate of the true value of the samples that were sent around. Luis asked, with several evaluations of bias, it is only referred to the same type, for example, CRM, or... yes, I think I have worded my slides not so well. Yes, Luis, you can do so that you use one CRM, then one spiking experiment, then maybe you find some reference method, etc. So yes, you can mix all those together. Yes, absolutely. Use all possibilities of getting some bias evaluations. Okay. So now U bias in turn is also composed of two components. One is root mean square bias. RMS stands for root mean square. I'll show you in the next slide what root mean square means. And UCref is the standard uncertainty of the reference value. So that, for example, if it was a certified reference material, then the reference value of that certified reference material also has uncertainty. That should also be factored in, because that you might be actually even more off, yeah, because the reference value itself is uncertain. No? True, usually UCREF is not the decisive component in this uncertainty evaluation, but it's still important. Yeah? And now, this RMS bias is the average possible bias of the laboratory results. So you've done a number of bias determinations. Each bias determination from replicates, yeah. For every individual bias determination, you do replicate measurements, and then you average them with root mean square averaging method, which I'll show you. And then UCREF is also the average of uncertainties of reference values that you use. In CRM, the reference value, of course, is on the certificate. No? In interlab comparison, you oftentimes don't have this uncertainty of the reference value. That's a tricky issue. I will give you some idea how to evaluate. And in spiking experiment, the uncertainty of reference value is how accurately you could measure the amount that you spiked, and how well do you think that you were able to disperse it into the sample the same way as the original analysis inside. Okay, and this thing here I've said now already several times. I think I don't really need to explain more. I see there's a typo. Not difficult, but difficult. All right. Yeah. So we speak about possible bias, and because of that, we might overestimate uncertainty because we give some additional uncertainty component which actually takes into account something that does not really. Now, how these root mean square things are calculated. First of all, every bias is this one, yeah, and the lab's value is here. Now, actually, I should put here explicitly in average, so it has to come from replicates, average. Let me make a change in my slide also. I want this average to be. Lab's average value when determining the bias, and this is the reference value. And now all these biases you take to the square. Those squares you sum up. This is the sum. Then this sum of squares you divide by how many biases you had, how many bias estimates, and then take square root. You may remember I said in the beginning of this course somewhere that most of the time when we speak about standard deviations, uncertainties, errors, biases, and all those things that refer to error or discrepancy in some way, we usually never add them as such, but add them as squares. Do all mathematical manipulations with squares, and finally take square root. So this is exactly this. So it's in fact simply averaging of squares instead of averaging the actual values. And now, what can anybody tell me what RMS averaging does differently from usual typical averaging. It does one thing very differently. Okay, let's assume we have two bias values, or just two numbers which we want to average. One is 1 and the other is 10. Arithmetic mean of 1 and 10 is 5.5. No? But can you now try to think what is the RMS of 1 and 10? Let's see. 10 squared is 100. 1 squared is 1. So it's 101. We now divide by 2. We get 50.5 and take square root of 50.5. Okay, you don't, maybe not so easy to make square root of that, but exactly square root of 49, which is very similar, happens to be 7. So that RMS averaging puts more weight to bigger discrepancies. It's very important. If you simply average uncertainties, you always get some underestimate, or you get lower things than with RMS average. This is why I'm stressing that you should not really just average, but you should do RMS averaging, because it puts more weight to bigger things. And this is also, like I already brought to your attention, I think the same thing that if you sum uncertainties, then also in the case of this squared summing, big components will eat up all the small components. Yeah? Like if you take the same 10, okay, 10 and 1, of course, are very, very different. But if you take 5 and 1, and you now sum them up, you get 6. But if you do this squared summing, you get 25.25 plus 1, and then square root, which is essentially still 5. So this 1 to 5 does not add. Okay, so this is what RMS bias is. And UC-REF is found exactly the same way as RMS bias, also by root mean square averaging. You take all the UC-REF values, take all of them to the square, divide by how many you had, and then take the square. This is the typical way how we do. Now, if it's an interlaboratory comparison that does not have an independent reference value, and this is mostly how interlaboratory comparisons are organized, then the simplest way to try to estimate UC-REF, the specific UC-REF from this one round, yeah, UC-REF is you take the between lab standard deviation, yeah, of that intercomparison, and you divide by square root of number of labs. But for example, if the standard deviation was something like 5 milligrams per kilogram, maybe 100 labs participated. Square root of 110, 5 divided by 10 is 0.5. This is how you do. And yeah, let me just repeat that every bias I value is from replicate measurements, yeah, which is pictured by this average. Arrow to. Okay. Yes, yeah, come on. Please, yeah, please ask it.
I have this question, for example, for the uncertainty of the reference values, as we can do like a lot of things at the same time. For example, we can use CRMs, we can use inter-laboratory comparisons. So all of these are done by doing replicates. So we can average all of them, considering the replicates and also different types of things into that value, right?
Yes. So for every bias determination, you first average your value. So this bias I is already obtained from replicates. Yeah. And then here in this formula, you have a number of those bias I values. So yes, yeah. And you can, yes, combine all of them. True, you can leave some out which you think are not maybe so relevant. Yeah, for example, if the interlaboratory comparison was really not well organized and there was so poor labs, huge scatter of laboratory data, then that's not really a good estimate. That one you perhaps should leave aside. So there's also some critical thinking involved, but in principle, yes.
For example, if we are using 2 CRMs, that will be included in that term.
Yeah. As will be also in the example that, let's see if we can start today. Hopefully we can start with the example today. All right. Any questions? There are questions. Carlo says there will be no negative squared biases. Yes, Carlo. I mean, bias itself can be either positive or negative. Both are very possible. But squares remove all those negative values. Kavintat says it makes every value to the positive. Yes. When people, if people want to average biases without squared averaging system, then oftentimes what they do, they average absolute values. So they remove all minuses. Otherwise, those biases can compensate each other so well that you end up with very, very small estimates. All right. Apparently, no more questions. Let's move on. Yeah. If you use only one CRM, or actually if you use only one source of a bias, something wrong? No problem. Have another screen. No. In any case, there will be one other picture, so you can choose which one you watch. Yeah. So if you have only one CRM, or actually only one source of bias, then this formula does not really work exactly like this. And then you should have this formula modified. And it takes then this form. So this is here your only bias estimate. This is the standard deviation of the standard uncertainty of the reference value. And here you have to additionally put in standard deviation of your measurement results that you got when you did the replicate measurements, all those bias determinations, and you divide it by n by how many you did. So that your, let's say, the reproducibility of your bias measurement goes into this as an additional term if you use only one. I would not at all recommend only one CRM. And in the past, I did not have this slide. I did not want to teach this formula at all. I still don't want to teach. But students who were very carefully reading the document said, but there's another formula. Why are you not teaching us that formula? Yeah, then I had to bring it. So the reason why it's here is for the very attentive and enthusiastic students, yeah, who found this and asked me why I'm not teaching. And yes, for the initial stage of method development, when you've just finished the development, you already want to offer some services, then you should use this formula for U-bias calculation. And here we just write bias, not RMS bias, simply because RMS bias means that there are different biases that you can average, but here there are not. It's just one single. And as I write here, use of one CRM is okay in the initial phase, but afterwards you should find more. And that more does not need to be another CRM. It can be also a spiking study or something. And here again, now similar things to what we had with URW. Ideally for separate, of course, you have to do that separately for every analyte. This is what you have to do. And then ideally, separately for different matrices, separately for different concentrations. This is pretty similar to what we had previously. And you really need quite some data, yeah? But luckily, a lot of such data that are needed for the Nordtest method are automatically available in the lab. So essentially every routine lab has to run control charts. So control chart data automatically comes in. You don't need to do anything extra. And labs have to be participating in interlab comparisons, and they are required to validate method, meaning they are required to analyze certified reference materials, so that even if not uncertainty estimation, they anyhow need things. So that this is one of the beautiful properties of the Nordtest method, that a lot of what you need is available automatically. And next interesting thing is here. If you remember, I said in ISO-GAM that if you miss some uncertainty source, etc., then you get underestimated uncertainty. Here, what happens, especially with bias, is that if you have poor quality reference values, like for example from interlaboratory comparisons, which is not really very good, then you tend to have overestimated uncertainty. And I would say that if you have to choose whether your uncertainty is significantly over or significantly underestimate, I would rather pick this overestimate. Then you can try to improve yourself and become lower. If you have underestimated uncertainties, you might be very happy with yourself. Oh, very good, very small uncertainty, don't need to do anything, until finally somebody challenges you that, look, your result is this. Other lab determined got completely different result. Because of your lab, I lost huge income. Yeah, now I demand you to pay me fine. Yeah, and so on. So it can become very serious with like, let's say, big industrial customers who use the analysis results for making economic decisions. Okay. And now, I think we are finally at the position when we, in principle, can start with the example. This roadmap attempts to picture all the formulas that you need. And now you can take from Moodle the Nordtest example, which is, check what is the name of number of that file. Yeah, it's 2.9 Nordtest example. You can take the initial or solved. They should be identical. Let me check. Some changes. Yeah, okay, yes, very nice. They are identical. I will freeze one screen with this roadmap. No, and then the other screen we will have example. We will perhaps not be able to finish today, but no problem. Because not so difficult, you can continue at home. And the next lecture, we can look at how you okay, I actually have here also the roadmap, but of course, no problem that it is in public. So, lead in polluted river water. No. And what we need to do, we have done this analysis. Our result is 43.0 micrograms per kilogram. And now we have to evaluate the uncertainty and assign the uncertainty to this. And as I already said, we should think about absolute or relative uncertainty. In general here, into all yellow cells, we need to write something, and green cells also need some writing. So we should fill those cells. And now here in this yellow cell, we should write whether absolute or relative. The information that will help you deciding whether absolute or relative is to some extent already available here, but to some extent we can calculate it in a moment. Any ideas, anybody, at this point already? Can already get some kind of relative. Why? Take microphone.
The ratio between the certainty and the concentration is quite close to each other.
You mean here?
Like the concentration is about 5 times higher, and the uncertainty is 4 times higher, closer in terms of relative uncertainty.
Very good, indeed. Let's see if we take, let's see how we can. Yeah, let's calculate the relative uncertainties from these. So this is now the absolute uncertainties, yeah. And let's note they are given with expanded uncertainty at K2. So for getting the relative uncertainty, we take this, divide by 2, and then do what? Divide by what? Yes, the reference value. Yeah. Okay. 0.85% is the relative uncertainty. Yeah. Here it's 0.73. If we now look, absolute uncertainties differ by how many times? 4 times. And relative uncertainties? 1.2 or 1.3 times, almost no difference. So here certainly relative uncertainty is more constant. But we can also look at how it is with lab results. So the lab has determined bias with 5 replicates. And we can now look at standard deviation of those replicates also, both absolute and relative standard deviation. So lab standard deviation equal to from I saved now. Can anybody check if when you try to open the saved file, will it have already these numbers in? I mean, when you try to open the solved file, will it already have these? Oh, good. Then all works. So here again, we see it's 4 times different in the absolute case. Yeah. And now we divide it by the average. Yeah, we can also calculate the average here. Now we calculate the relative standard deviation. Yeah, and I think we all agree the picture remains pretty much the same, that the relative values are very similar, but absolute values differ by several times. So that here, the decision is very simple. Here it is clearly relevant to use relative uncertainty. Put here relative so let me stop for a moment. I wrote relative here as a response to that question, yeah, so that we will. Did you manage to keep pace, or was I too fast? It's actually very simple calculation, yeah, not at all difficult. Why I did maybe. Okay. And now we can start with the random effects with URW. And here are some data from control chart. Not so many data, but okay, yeah, it's for the sake of this calculation exercise, it's of course good. Average. Standard deviation. And relative standard deviation. Probably we are not. I guess it's not really difficult, but let me a little. So did everybody manage to get these values the same values? People on the internet, are you managing to keep pace? Okay. If anybody lags behind or is unhappy or I'm too fast, etc., then immediately shout, yeah? So we now have done this yellow box. So the yellow box is finished. Now we take this blue box. Blue box in the roadmap. Well, actually already done quite something. Now comes the question, how do we find bias I in absolute terms? How do we find bias I? Who can teach me? How do we find bias I?
The deviation, RMS.
The difference between lab standard deviation and
RMS.
But where?
0.3 and 1.
No, not correct. Again, if you look what bias means, bias is not difference between errors or standard deviations. Bias is difference between measured values. Oh, anybody else wants to say? Maita. Take microphone also. Yeah.
The difference between lab result and difference material value, then where all those difference divided by the number of bias determinants.
But if you look here, do we really need to do it in so complex way? You see, when we later on average biases, we do this RMS thing, yes. But now when we are only calculating bias, and if you now recall what bias definition is, it's the difference between average lab value and reference value. So that per time, yeah, who can teach me what I write in cell B38? Yeah, Komal, yeah.
You can take the average of all the lab results and then you subtract it from like the reference value, that's 17.
Yes, we subtract from lab average the reference. Most of the time in bias calculations, you subtract, you first put like lab value and minus and reference value. For this uncertainty calculation, it doesn't matter which way you do because later on it's all squared. But it's like more correct to subtract reference value from lab value, not vice versa. Yeah. So let's do it. Oops, yeah, done. -1 microgram per kilogram. That we can put here. And how can we now find the relative bias I, those individual, like relative biases? The bias, absolute bias value divided by, yeah, interesting. The lab average or reference value, which one? Usually it is the reference value. When we calculate relative values, it's sometimes very tricky. Yeah, if there's a difference and you calculate relative difference, then what do you take as 100%? And sometimes it is not so clear. In this case, we are calculating actually bias from reference value, how much we are biased from reference value. So we divide by reference value. And also another consideration, when it's not clear which one to take, you should take the one which is more reliable. And the reference value probably is more reliable than that. So we divide this one by the reference value. Oh. And copy here. Oh. So we see that, yes, we are biased quite a bit, yeah. Okay. Now, it's 11:44. Oh, it's already 11:45. Meaning we stop here now, and you have all the freedom to complete this example at home. Not so difficult. Yeah, you follow the roadmap. You fill the yellow cells and then you fill the green cells. Yeah, here. And next time we will then compare these results with you. And also, there's a homework about Nordtest. It is the last one in the list, yeah, because in the past I had Nordtest part later on after CRMs and all those things, but now I brought it closer to the beginning. So you can already now also do Nordtest homework. By the way, let me tell you that there is one person who already has completed all homeworks, even those later ones, which we even haven't really done here. Yeah, so I'm not sure whether I'm allowed to say who that is, but big praise, yeah, to him, and very, very laudable. Yeah, person has been really, really enthusiastic and good. All homeworks done already. Yeah, Gleb.
So I wanted to ask about estimating bias in this example. So as we can see, we have relative bias of around 6-7%. But if we look on the average result of the sample and what the result of our lab is, then the relative bias is like 3-4 times higher. Are we allowed to use those biases in our calculation in this scenario?
Say again, what is 3 or 4 times higher than what?
So our result is 43 micrograms per kilogram, and the average value from the control charts is 55. So relative bias there is a lot higher. Yet,
you mean that this bias is high, but this value, the reference value, also is very high? Is this what you?
No.
Then
I can explain later on. I guess it doesn't matter.
No. You can explain now. Yeah.
So you see those values left.
Yes. Yeah.
And if we compare it to the result of 43
Yes.
G2, then there, if we calculate the bias, then relative bias will be around 22%. It's a lot higher than the values we get from analyzing certified reference material.
Now I got it. So your interpretation is that this value should be comparable to these values. Yeah, that this is the same sample.
So
is that your interpretation?
They shouldn't be off by more than 6 or 7%.
These are completely different samples. How good that you asked. I've been doing lousy job of explaining. Yeah, look, all this is here. All these values are our control chart sample. This is the big pile of, okay, in this case not meat, but river water that we put into some freezer, etc. But this value here is from a customer sample, which is a completely different sample. Yeah, customer brought it to our lab for analysis. They absolutely don't need to agree. Yeah? Did you get it?
Absolutely.
How good that you asked. Because maybe other people also had this.
Not that you've done a lousy job. I've done a miserable.
The result of a customer sample. Wow, now it's much better. Yeah. No. Okay, I need to. Customer sample. Almost. Wow. Now there is no confusion.
Clarify one last time, those values on the left, they are purely for estimating random effects.
Yes.
Or an uncertainty of random effects.
That and also for routine quality control, meaning that every day when you run your method, you see, aha, okay, I'm again getting 50 something, so probably my method is running okay. Because if on some day instead of 50 something you find 22, then you're, something wrong, I have some losses, our instrument not working correctly, etc. So these are on one hand for quality control, on the other hand, for uncertainty values. Did I answer? Good, very good. Now, the file got better because now it's better explained. Yeah, so this is customer sample result, yeah, 43. And these are control chart samples, which are completely different things. I don't have to agree. Okay, but with this, we now close, and we then meet again next week. And hopefully you by then already have finished this example and perhaps even the homework. Yeah. So you are welcome to try the homework. As you remember, there is no penalty for wrong answers. You can have as many attempts as you want. Thank you. Here we close.